Alright, so in this video, I'm going to talk about Euler's, Euler's identity, which is e to the I pi is equal to -1. I think this is a cool identity because you have a real number like e to the pi and you raise it to the I and you get, which is imaginary, and you get another real number out of it being -1. And in this video, I'm going to show you how to do that. To get that, you need to know something called Euler's formula, which is e to the I theta is equal to cosine theta plus I times sine of theta. And I'm going to prove that right now. So to do this, you need to know the Taylor series expansion of e to the x, which is e to the x is equal to this from k is equal to 0 to infinity of x to the n over n factorial. So basically we're going to put ix in a replacement for that x right there. So I'll do this right here. So e to ix is equal to the sum infinity, I'll use a k for the index, of ix n over n factorial. Okay, next what I'm going to do is I'm going to split this sum into two sums, one with the even terms of it and one with the odd terms. So I'll explain. We make a chart. So I'll have 2n and 2n plus 1. So if we want to split, if we want two sums, one with the even terms, one with the odd terms, we're going to use two separate terms. We're going to use 2n and 2n plus 1. So I'll give an example. If you do n is 0, 2n is 0, also 0, 2n plus 1 is 1. If n is 1, 2n is 2, and 2n plus 1 is 3. If n is 2, then 2n is 4, 2n plus 1 is 5, and if n is 3, 2n is 6, and 2n plus 1 is 7, and so on. So those will cover all of the terms of k in this sum, but we'll split it up into two separate ones. So I'll say it's equal to sum n equals 0 to infinity of ix, so that's 2n, and those will cover the even terms, over 2n factorial, plus another sum from n equals 0 to infinity of ix to the power of 2n plus 1 over 2n plus 1 factorial. Next, we're going to take these i's out of the, we're going to multiply these i's out of this parentheses. We'll do that right now. Sum of n equals 0 to infinity of, so this is going to be I to the 2n times x to the 2n. So I 2n x to the 2n, 2 factorial, 2n factorial, plus another sum, infinity of I to the 2n plus 1 times x to the 2n plus 1 over 2n plus 1 factorial. Next, we know with an exponent we can turn it in this I to the 2n into I squared to the n. So I'm going to do that just for this one right now. So let's bring it down here. It's equal to the sum from n equals 0 to 3 of I squared to the n. And we know what I squared is, that's -1, so I'm just going to replace that with the -1 to the n. -1 to the n, x to the 2n over 2n factorial. Now let's do the same thing for this term. We have a 2n plus 1, and if you know, if you add two exponents, you actually multiply the base. So you'd be I to the 2n times I to the 1. So let's do that. Plus sum from n equals 0 to infinity of, so I to the 2n we already figured out is -1 to the n. -1 to n times I to the 1 is just I. Times I times x to the 2n plus 1. X to the 2n plus 1 over 2n plus 1 factorial. We're almost there. This I is a constant in this sum, so we can pull it out. So let's do that. It's equal to sum from n equals 0 to infinity of -1 to the n x to the 2n over 2n factorial plus I times the sum from n equals 0 to infinity -1 to the n x to the 2n plus 1 over 2n plus 1 factorial. Now you might recognize that these two sums are actually the Taylor series expansions for sine and cosine. So this right here is cosine of x, and this right here is sine of x. So this is going to be equal to cosine x plus I times the sine of x, which is equal to e to the ix, which is our Euler's formula. Next, we can use this to figure out why e to the I pi is equal to -1. So I'll do this right here. So e to the I pi is equal to cosine of pi plus I times the sine of pi. So it's I to the sine, I not to the I times sine of the pi, sine of pi. Cosine pi is -1. Plus I times sine of, not sine of theta, sorry. Sine of pi. Sine of pi is 0, so e to the I pi is equal to -1. Sometimes you might see this written out as e to the I pi plus 1 equals 0, but it's the same thing. So that's about it. If you're wondering, this Euler's formula has to do with the unit circle and the real and imaginary plane. So if you have real numbers and imaginary numbers, if you were to plot z equals e to the ix, it would actually be a unit circle, just like the unit circle in like x and y plane. And that's about it. I think it's really cool that you can take, like, if you do e to the I pi, that's the same as e to the pi parentheses to the I. I think it's really cool that you can take a real number like e to the pi, raise it to an imaginary number, and get another real number out of it. And that's it.